So I'm going to talk about AGI. I've got lots of slides, so I'll move fairly quickly. There's a report I wrote for Riley. There's a company I started as an AI consulting company. And so what are we going to talk about? So the first question we have to ask, and I apologize if you've seen this talk before, I have given it a few times, hopefully there's no one in the room who has. What is intelligence? And then what physical systems are available for us to get inspiration from, and how far have we come in building, the hardware? And then I'm going to look at, very briefly, deep learning just ask very quickly the question, are we on the right track? And then with deep learning, is that going to get us all the way to AGI? The answer is no, spoiler. And so what do we need? What's missing? I'll do a very quick overview at the end. And we'll look at one theory in particular called active inference. And amongst a whole zoo of theories, really, AGI theories, we'll pick that one out. I'll explain why. And then I'll wrap it up with conclusions. So, why do we want to build it? Well, it's kind of obvious, right? We want to build it to solve the problem of the century, probably, of the human race, maybe, arguably, some might argue. And then, to make lots of money doing it. But really, it's just to solve it and see. And then once we solve it, as DeepMind said, we can use it to solve everything else. That includes all of science, all of medicine, help us live longer, healthier lives, new materials, you name it, spacecraft, explore the galaxies, use your imagination. So that really is the aim, right? To build general level intelligence, then quite quickly, move beyond that to super intelligence. So, quick question I always ask the audience, are any of these general intelligence? So we've got Watson there, super impressive. We've got the chess playing Deep Blue, IBM, AlphaSpar. Just very recently, DeepMind built that system that could beat some of the best players at StarCraft, an online game, and AlphaGo. So, no matter how impressive all of these are, and they certainly were, years in the making, 10, 20, 30 years since the birth of AI, maybe, they're nothing to do with AGI. So, and here's why, because intelligence is much broader than that. Remember, we asked the question, what is intelligence? Well, a guy called Howard Gardner at Harvard, I think in the 90s, wrote down quite a nice way of categorizing it. So you broke it into 9 categories. So we've got naturalist, understanding nature, the external world, can go do that, no. And I won't keep going, can go do that. If the answer is no, right? The spatial visualization. So we have AI, that can do maybe one of these really well, but never more than 2, right? So we're nowhere near AGI. Interpersonal, introspection. There's a TPU sitting in a Google data center. No matter what algorithms you run on it, it doesn't go, why am I here, right? Why am I a TPU? Who made me, right? No. This is all part of intelligence. Introspection, even though I make light of it, is a very important aspect of intelligence. Language, linguistics. We have NLP. We can have things that read and classify sentences, and are they creative? It's mostly based on statistical analysis of words and images and pixels and whatnot. It's not quite how the brain does it, or the biological brain. We have movement. The best athletes in the world get paid. These football players getting transferred for 100, 200 million pounds, right? I mean, they're some of the highest paid people in the world because they use their body so well. The basketball players in America, the football players in Europe. So that's a part of intelligence. And we have robotics, right? So there's no way, we haven't built any robots that can play football like Messi or the Michael Jordan at basketball. Nowhere close. Although impressive progress has been made with that. Let's just see it doing backflips and whatnot. It's super impressive, right? But not quite general, even in that one small limited sense. Interpersonal, how we communicate with each other in the world, animals, ourselves. Interpersonal communications, modeling what the other person is thinking, right? And then predicting what their next move will be. Nowhere near that. Existential, that's the why we're here bit, and the logical mathematical, that bit we've kind of got. I would argue we're quite good at chess and Go and numerical stuff, and a calculator can out-calculate almost every human being. It's a very simple calculator, so we probably we're okay in that quadrant. And then musical and other art, music, writing poems, just but mostly musical. Writing would be linguistic. So art, the creative fine arts. AI, narrow AI has written some songs, but I use the word written very loosely. One could argue again it's statistical, not creative. So what are we missing? So how far have we come? Well, like I said, the highest is probably logical, mathematical at 50%. So calculation's great, but not creativity. They can't really invent new games of Go or new types of math yet. Okay. The best mathematicians in the world, the guys who get the field medal, they can't, do math at the level of a field medalist or a Nobel Prize winner. Linguistic, as good as they are, it's in creating stuff and complete sentence completion and sentiment analysis. It's a statistical analysis. It's not what we're doing. It's not a creative thing. And then on through the list, right? Spatial, we've got the SLAM and body, you've got Atlas, in understanding the environment. I put 10%, that's a generous 10%. Music, Google Magenta, 50%. These are all pretty generous numbers, I would say. So basically, we're nowhere near general intelligence. We're not at 100%, but we can do all of these really well. And, we specialize in what we pick what we're good at and specialize, but we can do them all. So it takes a village to, raise a child, and it's going to take a village to create AGI. So we're going to need computer science. That's the one that everybody's got right now. But we're also going to need physics. We're going to need neuroscience, and we're going to need psychology. We're going to need people from all walks of life because that word general means general, right? It's everything. And so let's move on now to the hardware. How far we got with the hardware, then we'll look at the algorithms and we'll put it all together at the end. So we basically look at, we have an existence proof, that's us. That's 3 pounds of wet flesh in our skulls. That's what's creating this general intelligence, unless you believe in something else. But, neuroscience, physics tells us that is all we have. So we are getting inspiration, maybe not enough actually, but this is where the first place, I would probably start looking at how nature builds intelligence, or how nature has built intelligence, even though it's had a little bit of a head start on us, like 4 billion years. Maybe you could argue the Big Bang, 13 billion years. We've only been doing it for about 50. But it's come up with this thing up here in our skulls that can come up with the general theory of relativity, play chess, play Go, drive a car, go shopping, raise children, create mathematics, do this, paint, everything that civilization has done, this little 3 pound thing up here. Given there's a lot of us, and we don't do it on our own, we do it collectively, but we're nowhere near there, are we, with AI, if we're honest with ourselves. So how does nature do it? Well, you start off with a single cell organism. This is where the definition of intelligence gets a little bit tricky. It's like, is that thing intelligent? It's alive, it's living, it responds to its environment. I would argue yes, it stays alive, manages to stay alive over billions of years even. Maybe it's more intelligent than us in that respect. We'll wait and see. And it reproduces. It can't come up with a general theory of relativity. So in some sense, it has limited intelligence, but it's still intelligent. So, what's that doing? Can we reproduce that? Let's start there. That's the C. elegans worm. It has 302 neurons. It has a central nervous system. It's an organism with the simplest nervous system, CNS, central nervous system, 302 neurons. We can build that today. We've got models of that. So that's sort of where we are in our, we have 80 billion, 100 billion neurons. We're at 300. Yeah, so we've got a little road to travel, but if we can kind of understand how that thing works, maybe we can extrapolate and scale a little bit. So we can't give ourselves too hard a time. In the last 10 years, we can model a C. elegans worm. We have the bumblebee, that's about 1 million neurons, and they can navigate and do little dances and tell the rest of the bee colony where the pollen is and come back and mate and stay alive. They're super intelligent. I would argue they're super intelligent, right? They cannot come up with the general theory of relativity, but they're still super smart. And we haven't got that far. And then there's these things, the wet, mushy bit in our head, 3 pound in our skull. And we're nowhere near that, even though, it's small, right? I mean, we're trying to understand the universe, the cosmos, the galaxy. We're kind of, doing a better job. We can't even understand this tiny little thing. I mean, it's not just. It's very, very clever. It's had billions of years to evolve. So, what are we missing? What's the math? What's the mathematical model to build something that can model or come up with math and model its environment, interpersonal introspection? How does that happen, right? That's what we've got to figure out. It's no small problem. So the first thing we notice from biology is it's hierarchical. It starts off with molecules, then neurons, cells, and then networks of cells, and then sort of subsections of the brain, all integrated, connected together wonderfully to create a whole brain that's a connectome. And, there's a part do math, there's a part do language, there's a part do an emotion, is there a part that creates music, is there another part that drives a car, another part that, or is it all sort of integrated? So that's the kind of inspiration we need to take from biology and kind of use that to build mathematical models and then actually build it in physical hardware. Because Simon said we don't understand anything unless we can build it, and I quite agree, right? We can write down any mathematical stuff we like. There's lots of models, metallic pits, all sorts of different models, but until we build it, we don't really understand. We don't know if it's right. It's just a theory. Okay, and then then we have societies which are kind of hierarchical too. We organize ourselves hierarchical in cities and countries and nations, etc. Right? Okay, so this is biology, super complicated, super complex, right? Do we have to go down to that level of complexity? Well, that's a good question. Or can we just start at the cell, the neuron? That's a bit of an open question right now. It's good to have open questions because it keeps, that's science. That's what science is about, okay? But then it sort of organized itself into about 2 million of these cortical columns. So the brain has some sort of substructure there. And it's quite common over the whole brain and the neocortex, the math part, the seeing, the hearing. So if one part of our brain, if we go blind or whatever through accident, those cortical columns are used to analyze the sound. So there's something very fundamental going on there. These are all clues from biology. There's a connectome. And there's our central nervous system, how it's all connected together. Maybe we don't need to build bodies. If we want robots, we do. But if we just want something that thinks really well, creates theories like Stephen Hawking, I mean, he's paralyzed, he doesn't get around, dead now, but I'm just saying that we only need the rest of that if we want to build a robot, okay? We're really focused on the neocortex, a bit in the skull. Okay, and there's the societal levels. So what have we done? What have we built with hardware? Okay, well, we've come a long way. We're up to about 10 billion transistors, and there's different types, CPU, GPU, the graph core, IPU, and the different types of, due to different data sets, basically. So if we want to understand environmental data, that's where we probably need something beyond the GPU. Because the GPU is really good at matrix multiplication, and the brain doesn't do matrix multiplication to understand and create, right? But deep learning does, so we do need GPUs for that and CPUs. But if maybe we need to go beyond in a different sort of hardware architecture, if we do want to have general intelligence. Okay, so there's a little nostalgia here. That's a Cray, 1976, over 40 years ago, 160 megaflops. How quaint! We have teraflops in our pocket now. So this is where we are today. We have, with Moore's law, we've had a factor of 1 million or so since then. So we've got the i9 Intel CPU, we've got the NVIDIA V100 Volta GPU, we've got the Google TPU version 3, which are absolutely petaflops, and we've got just beyond the TPU coming online is the graph core IPU. But really, these are all matrix multipliers. So super impressive. We've got 100 petaflops in a thing that, will fit on the stage, which is far more what the brain does. I think the brain does about a petaflop or so. So it's not about raw computation, right? If it was, we would be there. This thing would be coming up with theories of relativity and all sorts of stuff, unifying physics and creating symphonies. But it can't. It's dumb as a brick, right? It sits there. Right, and so is that. That's exaflops, right? That's 1,000 times a petaflop. So we're going to need something more. What are we missing? in the hardware, right? So it's not just about algorithms, it's actually about the hardware, which is pretty obvious when you think about it, because what's up here is a little different than the hardware we just seen. What about neuromorphic computing? So this is where things get interesting, because now we're using analog circuits, which is what the brain is. The brain uses spiking neural networks, which is almost a combination of analog and digital. So there's a guy called Steve Ferber, one of the co-founders of ARM. After 20 years, he left ARM and University of Manchester 20 years ago. He set up a project called Spinnaker, which has now been folded into the Human Brain Project. There's IBM True North. There's brain scales at the Human Brain Project. There's various projects throughout the world building these this analog hardware, right? So for me, I think this is a big part of it. Okay, algorithms are certainly important, but I think the hardware is important as well. So Spinnaker, we've got 1 billion neurons, so 100 times that we've got the human brain. So we've built a mouse brain already, and it can do stuff like navigate through mazes and play Sudoku and do crossword puzzles. It does intelligent stuff, and no one in some people in the room have heard about it. But it does not get the press, does it? DeepMind does, and AlphaGo, and everything else. It doesn't. But I can argue that this is part of my thesis, that this is what will take us to general intelligence. And there it is. 5 racks, we're up to 10 now. There it is, sitting in a data center in Manchester, part of the Human Brain Project, and that is neuromorphic computing. There's 1 billion neurons there. There's a mouse brain right there. It's a little bigger than a mouse brain, but we've seen with Moore's law, we're quite good at scaling, right? So the point is, we've built some stuff here which might be useful for us. And that's how you scale up. You put 1,000 neurons on a core. You put 18 cores on a chip, you send it away, you get it built, it comes back, you put them together, put the chips on the board, put boards in a rack, and then get 10 cabinets and put 5 racks in each cabinet. You've got 50 servers, neuromorphic servers, and you have a mouse brain. That's how you do it, and it's been done. That is the brain scale project I mentioned at the Human Brain Project. That's about the same size as the Spinnaker and the same power, about a mouse brain. Uses a slightly different architecture. I won't go into the details. True North IBM uses a slightly different architecture, but the point is they're all neuromorphic and they're all analog based on spiking neural networks. And that's sort of general intelligent mouse level compared to the Google TPUs, which are super impressive at different types of things. But I'd argue they won't get us to general intelligence. There's the thing on the left. What about quantum? I don't think the brain is quantum. It's too warm and wet. Quantum needs super cold temperatures. It's decoherence very quickly. I don't think there's qubits in the brain, but they look nice. So I put a picture of one on there. That's what a quantum circuit looks like. So, suddenly we're not just got the CPUs anymore. We've got, these 4 different types of architectures, and one's biological, one's quantum, or 3 are non-biological. We've got quantum, we've got neuromorphic, and we've got the digital. And I'm arguing that the thing on the top right will be needed for general intelligence. And here's what they look like. We've built them all. The quantum, that's a 7-bit IBM qubits, 7-qubit IBM processor, quantum processor. There's a neuromorphic, that's what they look like microscopically. There's a digital, I mentioned 10 billion on a chip, on a processor, whether it's CPU, GPU. And that's how biology looks like. So, I think the neuromorphic in biology, the neuromorphic will map onto the biological the best out of all of those options there. Not to say the others aren't clever. So the data centers of the future, they'll look like this. We won't just have them fill up with CPUs, GPUs. We'll have neuromorphics, we'll have quantum, and we'll have a little bit of classical as well. So interesting times ahead. Deep learning, just going to have a couple of slides here. There's this plethora of neural networks. It won't get us there. They're very good at classification and regression and pattern matching. They're very good at this matrix multiplication. This is all statistical analysis, very clever, but nothing to do with what the brain's doing at all. And so this is a TensorFlow meetup, so I had to mention TensorFlow. Here's how popular TensorFlow is. So if you're going to start on the deep learning, you need to pick PyTorch or TensorFlow. Okay. So that's that. There we go. So what do we need? How do we build AGI? So Well, I would start, as a physicist, I would start with the laws of physics. And we've come along, physics is an old subject, about 400 years old. Computer science is quite new, about 70 years old. So I would just go back and start with the laws of physics. And, what are the laws of physics? Because the brain, I would argue, is a physical system. So probably that's the best place to start. Don't just start writing a JavaScript. No, go back to basics. This is what physics is. And basically all of physics, and maybe not too many people in the room know this, can be written as principle of least action. S is the action, L is Lagrangian, blah, blah, blah. I did graduate level physics, so I know this stuff really well, drilled into me, hundreds of exams and assignments and blah, blah, blah. And there's been a book just recently called Principle of Least Action, which surprised me. So it sort of has chapters on each section of physics and how you can derive it from delta S equals 0. So I would start there if I was going to build an intelligent system. So that's the physics. What else do we need? So intelligence isn't just about pattern matching. I've conveyed that already. 9 different types. Only one or two types is about pattern matching, really. It's about modeling the world, really. That's what intelligence is. It's how well we can model the world and then make predictions and predict the next step. That's how we make money. That's how we stay alive. That's how we do everything. That's what intelligence is, by definition, really. We can play chess and do all sorts of things, but really chess is about understanding our environment, modeling our the ability to model our environment, and to make predictions and then to take action on those predictions. Okay? We need to explain and understand what we see. This is what we need to build. We need to imagine things, and we need to problem solve and plan actions. We need to build new models as we learn about the world. Nothing to do with AlphaGo, nothing to do with Deep Blue, nothing to do with AlphaStar at all. Okay, I would argue they're super clever, but they're statistical. They're not really intelligent. Okay, so what is intelligence? Well, there's loads of theories. I'm going to pick out active inference, but there's a ton of work, and all of these people have been doing this work for 30 years now. There's Schmidhuber, Hutter, Bialek at Princeton, Tishby, and Friston at UCL here. This is their life's work. They're mad scientists toiling away, but sort of it's starting to happen for them. So they'll probably get to see a little bit of, the fruits of their labor. Okay, so what is active inference? That's one I picked out. You're more than welcome to go home and Google all of these. They're all got papers on archive. They've all got wonderful websites. There's loads and loads of beautiful, brilliant reading if you're interested in intelligence, essentially, right? And how we might get there. And they all have useful input, and we don't quite know which one is right. Maybe it'd be a combination of a few. But this is what Friston's saying. It's called active inference. It's based on physics and information theory, so it's a very fundamental theory. It uses something called the free energy principle, and it does encompass all space and all time scales. So, yeah, it works from the very small to the very large, and it works from nanoseconds to the age of the universe. So it's completely general. Yeah. Now, I don't expect you, there it is there. I don't expect you, to go, I get it now, because this is hard stuff and it takes a lot of reading. It certainly took me an awful lot of time, actually, to read through all of these different theories and just start at the basics with computer science. Remember I said it took a village, neuroscience, physics, psychology. I just learned a lot about a lot of things, right? And we do. This is why it's a hard problem and it hasn't been solved yet. So this is how he sort of puts it down, models it, I guess. So the free energy principle, you just divide the world into internal states, which is our brain, and outside the environment, agent environment. Anybody who's ever done reinforcement learning, it's a similar sort of thing, right? You have the agent and the environment, but this kind of explains how the agent works itself, what's going on inside the brain, what's going on outside the brain. It's separated by something called a Markov blanket, which is quite a cool sounding name. A guy called Judy Pearl at University of Southern California came up with that in the 80s. So, there's contributions from everywhere into this theory. And so it works from, like I say, small to large. It works from cells to brains, external states, internal states, whether that's a cell, microscopic. When we saw the cell, I argued that was intelligent to a brain. The difference is the brain is much more complicated internally than the cell. It's got 10 billion neurons. The cell's got none. But it's a similar setup, and so you can kind of, at all different scales, mice, people, bacteria. Okay, there's the math. The math gets ugly. That's what it looks like, but if you've ever read a reinforcement learning paper, that's what that looks like as well. So, you know, if you're a deep learning researcher, the only difference is these are physical quantities like entropy and things like that. The reinforcement learning, these will be much more statistical, but they're kind of similar looking probability distributions, but this one's based more on fundamental physics and information theory. Okay, don't expect you to take any of that in, I just wanted to show off the math. But yeah. So how clever am I? Look at that math, but I didn't do it, it's not mine. Okay, so can we build it? Well, yes we can. We have the theories. We have a few candidates. We have the algorithm. We even have software. All of, the Professor Frisson has a big software base that has been developed over the years. We have the hardware. I'm going to argue the neuromorphic hardware is there. So if we run this on Spinnaker, we should be good. And we have data sets. It's a thing called the internet. We have all the data we need. And so I would say, to some extent, we're kind of there. We have the mouse brain, and we have, you know, the active inference running on it. And I'd say we're kind of there. We're kind of in the very early stages. We're not millions of miles away, 20 years away down the road. We're there. We're on the road, the exponential road at the very beginning. I don't think there's anything missing. There's no theory missing. There's no hardware missing. There's no data missing, and there's no. We have a theory. That's a big statement, right? So I think we're there. Okay, so what do we need? We need hardware, better hardware. We need a TensorFlow for general intelligence. So if any software engineers here in the room want to get started about building, you'll become famous. And yeah, it's a Apollo project about time. I mean, you know, it's the one, right? We've got to solve intelligence and then use it to solve everything else. There's other DeepMind, the brain, the Human Brain Project. China just invested $10 million in setting up a city, the whole city to develop AGI. And should we build it? I mean, there's ethics, there's safety, but I'll leave that to another discussion. Finishing off, here's some AGI projects that are real, they exist, they have venture funding, they have people, they're working on it 24/7 every day, that's their life, that's what they do. You know, I did put DeepMind up there, some of them are well known, some not so well known. Some are smaller, some are bigger. And so, in conclusion, it's obvious to most that deep learning is lacking the foundations needed for general theory of intelligence. It's based on statistics, not physics. Some groups are starting to look at bioplausible models, and it frustrates me that they weren't starting looking at them all along. Some were, but a lot of this deep learning stuff is just, you know, it was never going to get us there. And people, you know, hopefully realize that now, but I'm not that optimistic. But I'm saying right now, it's not going to get us there at all. And is it? Yeah, I've already said we've already got it. Not human level, but mouse level. And Neuromorphic might be the platform to get us there. And I'll leave you with this parting words from Jeff Hinton. Okay, so what he was saying there is basically what I think the godfather of AI, of deep learning from the 80s, and his whole life, used to work with Frisson at UCL, by the way, went to Toronto in the end. What he is saying is that deep learning won't get us there. It was never meant to. I didn't make a mistake, it's just I was working on something else. What we do need, what will get us there, is understanding the brain. And this is in 2016, he's saying, I think that we are very close to that moment. And I've put up a few theories there, which maybe he wasn't even aware of. Maybe he was, he's a smart guy. But I believe we do understand the brain. I believe we're there. Thanks.
Great stuff. Round of applause. Okay, good stuff. So we're a little bit tight for time, but I'm curious. So you've been a research fellow. You've obviously been running deep learning partnerships for quite a while now.
Yeah.
What is your interest? How come so much focus or interest in this? And where do we find you online? And what's your next project?
Yeah, so I have started a company called TuringAI.co, and
which was up there, right?
Yeah. May not have been actually.
It was one of the boxes up there.
Yeah, it was actually one of the boxes.
Tell us about that.
Yeah, Turing, like as an Alan Turing AI.co. Now, I've actually started that company with Professor Friston and a couple of very clever postdocs. So we're working on this. Schmidt-Huber's working on it. Violek at Princeton's working on it. DeepMind are working on it. So I'm not saying that we're going to crack it first, but yeah, we're very involved in solving the problem.
Big respect. Well, with you all the way, and we'll have you back on TensorFlow London once you solve that problem.
Yeah.
Okay, cool. We've got time for 2 quick questions. Anyone in the crowd? Okay, gentleman there. Introduce yourself.
Hi, my name is Atul.
Yeah.
I have a quick question regarding Spinnaker, the one you mentioned which gets less publicity. Given that DeepMind 0 could beat Deep Blue within 9 hours of learning, why isn't there something similar being done to promote it?
Yeah, so I mean, I don't know really. They're using reinforcement learning and Markov, Monte Carlo's tree search basically, right? So I'm not trying to take anything away from any of that work. It's brilliant, right? Just like a calculator can out-calculate us at multiplying 2 large numbers together, they can, there's no way we're ever going to beat them at chess or go ever again, right? It's super clever stuff. But remember my 9 types of intelligence, they can't do anything else. AlphaGo can't write a symphony. You need a different algorithm for that. So, how do you integrate them all together? I mean, that's a pretty big problem.
Yeah, thanks. Any other questions? You have it there. Why don't you introduce yourself?
Hi, my name is Dimitri. I was just wondering about the Spinnaker project. I was just wondering, what's the neuron interconnectivity compared to the mouse? I mean, yeah, the number of neurons is the same, but is the connectivity, is that different?
Yeah, nothing like it. So that's a great point. So there's 2 metrics, isn't it? It's the number of neurons, but it's also the connectivity between the neurons. So the biology seems to do it. It likes to connect about 1,000 to 10,000 synapses per every neuron. So Spinnaker is nowhere near that. It might have a few dozen. So that's a very important metric. Right? Connectivity is super important too. Yeah.
Great stuff. Time for one more? There's one over here. Mark.
Hi, my name is Marco. I work at an AI startup called Neuron. My question is, you focus a lot on the CPU architecture, but obviously the Church-Turing thesis says that any function that is computable can be executed by any machine, whether biological, whether the CPU, whether the GPU. Is it just the execution speed that you care about, or do you see anything wrong with the Church-Turing thesis?
No, I do believe that's a great question. And there's been a lot of debate, even philosophical debate, about whether the brain is Turing complete. And I think it is. And most people do as well. So it's a very fringe people who say there's something else in the brain that's not Turing complete. So I don't believe there's any bottleneck there at all. I just think it's a different type of computational system.
We can apply general intelligence with any type of CPU.
Yeah, I still think we need the synaptic connections, like 1,000 to 10,000. So it really is a deeply embedded hardware problem, right? But that hardware is Turing complete. Yeah. So the general theory of computation applies, but it's just a different hardware. That's a good question. Yeah. Okay. Thanks.